In the summer of 1944, during the Allied advance through France, the rhythm of progress slowed to a halt on the banks of the River Vire. The front was moving eastward after the breakout from Normandy, but every bridge that once spanned the French countryside had been blown apart by retreating German forces. Steel beams jutted from the water like broken ribs, charred timbers drifted downstream, and the smell of oil and cordite still lingered in the air. American armored units stood idle on muddy roads, engines silent, waiting for the engineers to find a way across. Time, more than enemy fire, became their greatest adversary. The 36th Engineer Combat Battalion was among the first to reach the river. Their task was simple in theory, but almost impossible in practice. Create a crossing strong enough to bear trucks and tanks without the standard pontoon equipment, which had been destroyed in a previous bombardment. The engineers surveyed the ruins, a chaotic mix of wrecked scaffolding, shattered stone, and the twisted remains of a Bailey bridge that had been half built before German artillery found its range. Supplies were thin, the terrain soft, and the current deceptively strong. To most of the men, the situation seemed hopeless amid the debris. However, something caught their attention. Scattered along the riverbank were dozens of empty 55-gallon fuel drums, discarded by German transport units during their retreat. Some still smelled faintly of gasoline. Others were scorched and dented from fire. To the average soldier, they were nothing but waste, useless metal littering the shore. Yet to the engineers, trained to see not what a thing was, but what it could become, those barrels represented something else entirely, potential buoyancy. The battalion's officers gathered near the bank, sketching rough calculations on maps and ration boxes. They knew that each drum, when sealed and empty, could support nearly 200 kilograms of weight on water. Theoretically, dozens tied together might hold a vehicle. It was an idea that defied logic, an act of desperation born out of necessity, and yet necessity was precisely what drove wartime innovation. The enemy was not far ahead, and every hour lost meant more resistance forming beyond the river. As evening fell, the engineers scavenged every usable drum they could find, dragging them from the reeds and mud. The sound of metal scraping against stone echoed across the valley. A few men shook their heads at the absurdity of it all. A bridge built from oil barrels, on which tanks were expected to cross. Still, orders were orders, and the Corps of Engineers had a long tradition of turning impossible tasks into practical miracles. By nightfall, the shore was alive with activity. Floodlights from trucks cast long shadows across the water as sparks flew from cutting torches, and the rhythmic clang of hammers filled the air. Chains, ropes, and lengths of salvaged timber were laid out in rows. The smell of diesel mixed with the river mist, and under the pale light of a waning moon, the shape of something improbable began to emerge. A floating platform anchored to the current, shimmering like a ghostly bridge between necessity and invention. By dawn, the work was complete. A narrow strip of planks stretched across the moving water, supported entirely by the buoyancy of more than 150 fuel drums. It was crude, untested, and, to most observers, utterly insane. But when the first convoy rolled forward and the bridge held under the weight, disbelief turned into silence. The absurd had become possible, and in that fragile, floating line of metal and wood, the ingenuity of war found one of its most unexpected triumphs. By the summer of 1944, the U.S. Army's engineer battalions were operating under relentless pressure. The Normandy landings had succeeded, but the real struggle began in the weeks that followed. Every mile of liberated territory brought new obstacles. Shattered bridges, cratered roads, flooded valleys, and rivers transformed into natural fortresses by retreating German forces. The Wehrmacht's systematic destruction of infrastructure was methodical and effective. When they fell back, they left behind nothing but ruins. For the engineers, progress meant not only keeping pace with the front, but rebuilding the very landscape beneath it. Standard bridging units, like the M2 pneumatic pontoon bridge and the prefabricated British Bailey Bridge, had revolutionized combat engineering earlier in the war. Yet in France, these systems were often useless without the logistical support they required. The heavy Bailey components needed trucks and cranes that lagged far behind the advancing spearheads. Pontoons were vulnerable to artillery fire and impossible to replace once destroyed. Ammunition and fuel convoys took priority over engineering supplies, leaving many units stranded with only the tools they carried. In the days after the breakout from St. Lo, the front line moved faster than its bridges could follow. The terrain itself compounded every difficulty. The rivers of Normandy were deceptive, narrow but deep, their beds coated with soft mud and concealed debris. Flooding from early summer rains had turned meadows into bogs, and every attempt to ford vehicles ended with engines drowned and tracks swallowed whole. Conventional bridging demanded solid anchorage, but the soil along the Vire and its tributaries offered none. A single misplaced support could cause an entire span to collapse. In many cases, engineers had to work waist-deep in cold, fast-moving water while under threat of enemy shelling. The men of the 36th Engineer Combat Battalion had already faced weeks of this grueling routine. They rebuilt what others destroyed, often under conditions so harsh that even victory felt mechanical. Their workload never stopped. They cleared mines in the morning, repaired roads by day, and constructed makeshift crossings at night. Exhaustion was constant. Morale wavered not because of fear, but because every success was temporary. The Germans destroyed as fast as the Americans built. When the unit reached the Vire, they found every conventional option exhausted. Even the river itself seemed to mock their effort. Its width was modest, yet its current pulled with unexpected force. Attempts to span it with timber trestles failed when the support sank into the mud. Rubber pontoon sections had been lost during transit or damaged beyond repair. What remained were a handful of steel cables, some planking, and whatever could be scavenged from the ruins of nearby depots. There were no cranes, no spare beams, and no replacement pontoons. The only things that floated were empty fuel drums, remnants of German supply lines, scattered like debris along the shore. At first glance, the drums offered nothing of value. They were dented, burned, coated in oil, and dangerously thin. A single misstep could crush them. Even the most optimistic engineer doubted their usefulness. A tank weighed over 30 tons. A single barrel could barely hold one man. The numbers didn't seem to add up. Yet necessity has its own arithmetic. The battalion's officers knew that waiting for replacement pontoon kits would take days, perhaps weeks, and command demanded that the crossing be opened immediately. Every hour of delay risked cutting the advancing columns off from fuel and ammunition. The engineers faced a dilemma that defined much of the European campaign, the race between destruction and reconstruction. German retreat was swift but deliberate. Every river was mined, every crossing sabotaged. The Allies had air superiority and overwhelming firepower, but those advantages meant little when armored units sat immobilized on a riverbank. The 36th Battalion stood at such a juncture, trapped between progress and paralysis, surrounded by the wreckage of conventional warfare. They had no factory-built bridge parts, no airlifted reinforcements, and no margin for error. It was under these conditions, when improvisation became the only form of survival, that the problem of the Vire turned from an engineering challenge into a test of imagination. What could carry tanks when all bridges were gone? What could float under the weight of war? The answer, as absurd as it seemed, waited quietly in the mud. Hundreds of fuel barrels, discarded by an enemy who never imagined they would become the foundation of a bridge. Since the early 20th century, the U.S. Army Corps of Engineers had relied on portable bridges to sustain the movement of modern armies. During the First World War, engineers learned that success on the battlefield depended as much on logistics as on firepower. Rivers, canals, and bombed-out roads could immobilize entire divisions, so bridging became an essential military art. The early systems, wooden trestles, pneumatic floats, and prefabricated steel spans, were refined in the interwar years into standardized kits like the M1938 pontoon bridge. Yet by 1944, warfare had evolved faster than supply doctrine. The armies that landed in Normandy needed flexibility, and traditional methods often could not keep pace with the fluid nature of the campaign. In Europe, destruction was the rule, not the exception. The German Wehrmacht, retreating methodically through France, practiced what was known as Versuchungskrieg, a war of delay. Every bridge was mined and destroyed. Every river turned into an obstacle. For the advancing Allies, this meant that engineers were constantly improvising under pressure. While the British relied heavily on their modular Bailey bridge system, the Americans favored a mix of steel treadway bridges, pneumatic pontoons, and When those were destroyed or delayed, sheer ingenuity. It was in this environment that the use of unconventional materials, barrels, doors, fuel drums, and even wrecked vehicles, became not eccentricities but necessities. By mid-1944, American engineering units had become some of the most adaptive forces in the war. Manuals like Field Manual 5 to 270, Bridging and Engineer Field Manual 5 to 5 encouraged initiative, urging soldiers to construct with what the field provides. In practice, that meant scavenging from the landscape. Rail ties became beams, telegraph wires became binding cables, and oil drums, ubiquitous throughout the European theater, emerged as a versatile flotation element. The standard U.S. Army 55-gallon, 208-liter, steel drum, used for gasoline, lubricants, and kerosene, weighed about 20 kilograms empty and could support roughly 180 kilograms of weight when sealed and floating. These drums were everywhere, on supply trucks, in depots, and abandoned along roadsides after bombardments. The first recorded experiments with fuel barrels as pontoons occurred not in France, but earlier in North Africa and Sicily, where American engineers from the 19th and 36th Engineer Combat Regiments used drums to stabilize rafts for jeeps and artillery pieces. They found that a line of barrels tied together with rope and reinforced with planks could create a surprisingly stable raft. However, these early improvisations were intended only for light loads. In Europe, after D-Day, the same idea would be pushed to its limits. In July 1944, during operations following the Normandy breakout, the 36th Engineer Combat Battalion found itself in a situation where all standard bridging materials had been destroyed or lost. The battalion had crossed the Weser River before, but the rapid German retreat left the banks mined and the infrastructure in ruins. When resupply failed to arrive, officers turned to the resources at hand: empty fuel drums salvaged from depots and wrecked German vehicles. The concept of using barrels for flotation was not new, but applying it to support armored vehicles represented a leap of both faith and calculation. The American approach to engineering during World War II was shaped by its decentralized philosophy. Field officers were granted freedom to adapt and innovate as long as results followed. The Corps of Engineers prided itself on this spirit. In training camps from Fort Belvoir in Virginia to Camp Claiborne in Louisiana, soldiers were taught that an engineer's weapon is his mind. Improvisation was institutionalized. By 1944, reports circulated across Europe describing bridges made from timbered farm wagons, steel oil drums, and even aircraft fuel tanks. The 36th Battalion's experiment near the Weser reflected that ethos. It was not an official project, nor did it follow any manual. It arose from necessity and the American habit of transforming industrial waste into military utility. A 55-gallon drum, sealed and roped together with dozens of its kind, could serve as a buoyant platform for trucks and light tanks if the load was evenly distributed. This understanding of physics and resourcefulness made possible what seemed unthinkable: a bridge capable of carrying vehicles across a river without a single manufactured pontoon. In hindsight, this episode fit neatly into the broader history of wartime innovation. The barrel bridges of 1944 were not miracles, but products of an engineering culture that thrived under constraint. They demonstrated that improvisation could be systematized, that creativity could coexist with discipline. These makeshift crossings symbolize a turning point in combat engineering, where the line between invention and survival blurred completely. What began as a desperate experiment by a handful of soldiers in Normandy would later be documented in post-war manuals as a textbook example of adaptive field engineering, a reminder that, in war, even the most ordinary object could carry the weight of history. The idea that would change the course of the operation emerged not from a blueprint, but from a moment of quiet calculation. Captain John Richardson of the 36th Engineer Combat Battalion had spent years studying bridge dynamics and flotation under combat conditions. Like many engineer officers, he carried with him not only tools but an instinct for improvisation. On the banks of the River Weser, surrounded by wreckage and exhausted men, he began to view the scattered fuel barrels not as debris, but as structural elements waiting to be organized. He knew the principle of displacement as well as any naval architect. A sealed container could bear far more weight than its own mass as long as its volume displaced water equal to that load. The empty 55-gallon drums, if tied together, could create a crude but buoyant base strong enough to carry more than anyone on the riverbank would believe. Richardson had seen similar experiments during his training at Fort Belvoir, where instructors had demonstrated makeshift rafts built from oil drums. Those were designed to ferry soldiers or jeeps, not armored vehicles, yet the same physics applied. Each drum provided roughly 400 pounds of buoyancy. 6 aligned side by side, properly sealed and reinforced, could support nearly 2,400 pounds. He quickly realized that if he grouped the barrels into rigid frames, distributed weight evenly, and controlled lateral sway, the assembly could form a floating deck. It would not rival a Bailey bridge in strength, but it could carry medium loads long enough to move the column forward. The first step was conceptual, the second logistical. He ordered his men to gather every intact drum within reach. They scavenged from abandoned depots and from the remnants of German fuel trucks, washing out the interior residue to prevent ignition. The barrels were arranged in clusters, 6 to a section, and lashed together using steel cable and salvage tow chains. Across the top, wooden planks from destroyed farm buildings were bolted to create a continuous surface. Richardson emphasized that the success of the structure depended not on brute strength, but on balance. The more evenly the load was spread, the less stress any single drum would bear. To prevent the platform from twisting in the current, he designed a lattice of crossbeams connecting each section. The bridge would consist of multiple identical modules, each roughly 3 meters wide, linked end-to-end by chains and supported laterally by ropes anchored to both shores. This modular design mirrored the principles behind the Army's treadway bridges, though improvised with whatever was available. When the first segments floated, Richardson noted how the drums flexed independently but moved as a unit, absorbing wave motion rather than resisting it. What appeared fragile was, in practice, resilient. For stability, Richardson had the ends of the structure secured with heavy mooring cables fastened to trees and buried stakes. He ordered sandbags placed along the near shore to counteract the initial shift when vehicles rolled on. Engineers adjusted the deck's alignment repeatedly to minimize tilt and drag. They reinforced the underside of each module with diagonal braces made from scrap timber to prevent torsion. The finished sections were light enough to be maneuvered by hand, yet strong enough to support a fully loaded truck. The completed span extended close to 60 meters, stretching across the narrowest point of the river. Its appearance was anything but reassuring. The surface wobbled underfoot, the drums groaned as water pressed against them, and gaps between the planks revealed the dark current below. But when tested under load, it behaved exactly as Richardson's calculations predicted. The weight distributed across dozens of buoyant chambers never exceeded the structural threshold of any single drum. In the absence of proper engineering tools, the captain had turned his understanding of basic physics into a functioning bridge. The structure's efficiency came not from sophistication, but from its simplicity. Each module could be detached, repaired, or repositioned within minutes. If artillery damaged part of the span, engineers could replace a section using spare barrels without dismantling the whole crossing. Its flexibility made it both adaptable and expendable, qualities essential to combat operations. What began as a desperate improvisation was, by design, an elegant application of first principles. Use available materials, maintain buoyant equilibrium, and rely on modular redundancy to absorb stress. By the time the last chain was tightened and the final anchor secured, the engineers understood what Richardson had achieved. He had transformed industrial scrap into a military asset by applying nothing more than reasoning, measurement, and courage. The bridge of floating barrels might have appeared absurd, but beneath its crude surface lay a mastery of improvisational engineering that would soon prove indispensable to the Allied advance. The construction began at dusk, under the fading light of a French summer evening. The engineers of the 36th Engineer Combat Battalion had neither proper materials nor time, but they had determination and discipline. As the last combat units secured the area along the WWII, the engineers set to work. Truck headlights and the glow of acetylene lamps illuminated the muddy riverbank, turning the scene into a field workshop under fire-scorched trees. Shadows of men moved back and forth, carrying barrels, tools, and planks, their figures mirrored in the black water below. The noise of war had faded into the distance, replaced by the metallic rhythm of hammers, chains, and the hiss of rope tightening against steel. Each section of the bridge was built according to Captain Richardson's improvised design. Teams of 4 to 6 men worked on separate modules simultaneously to save time. The first task was to clean and seal the 55-gallon drums. They were rinsed of fuel residue with river water and sealed tightly with improvised plugs made of wax and rubber from damaged tires. Any drum that leaked or dented beyond use was discarded immediately. By nightfall, more than 150 drums had been salvaged from wrecked depots and abandoned German fuel trucks nearby. Once prepared, the barrels were arranged in parallel rows, 6 across, their ends aligned and bound together with steel cables and heavy tow chains. To keep the drums from rolling or shifting, engineers inserted wooden spaces between them, wedging the assemblies into rigid frames. Over the top of each cluster, planks scavenged from barns, bridges, and even furniture were laid to form a deck. Nails, bolts, and wire were driven through the wood and into metal brackets welded from scraps. Every available material was repurposed. Engineers worked with whatever tools they had, sledgehammers, crowbars, and field saws meant for timber cutting rather than fine construction. As sections were completed, they were dragged to the shoreline and slid into the water, using rollers fashioned from fallen logs. The first module floated unsteadily, bobbing in the current, but remained stable once anchored with guide ropes. Encouraged, the men launched the next, linking it to the first with chains and locking pins. One by one, the modules extended across the river, forming a flexible but continuous path. The engineers moved carefully along the narrow surface, adjusting tension and replacing planks where gaps appeared. The current pushed against the structure, making every step precarious. A single misbalance could have torn the bridge apart, yet coordination and training kept the process methodical. To counterpull the water, Richardson ordered heavy mooring lines fixed to the trunks of nearby poplars and reinforced with sandbags. Along both banks, men hammered in steel stakes to hold the anchor points. Ropes ran diagonally from shore to shore, keeping the bridge from drifting downstream. The sound of chain links striking metal echoed through the misty night. Occasionally, bursts of distant artillery rumbled on the horizon, but the work continued without pause. By midnight, half the river was spanned. The bridge creaked and swayed, but the buoyancy held. Engineers tested each section by walking across in pairs, listening to how the structure responded to their weight. Every adjustment mattered. A plank too loose, a rope too slack, and the entire line could twist. They reinforced joints with additional braces and replaced weak boards with thicker timber. When water seeped into one of the barrels, a diver waded out, resealing the leak with pitch and canvas. Nothing was wasted. Every broken piece was repaired, reused, or reimagined. As dawn approached, the men were covered in mud and sweat, their hands raw from rope and wire. Yet the outline of the bridge was complete. A single continuous line of floating modules now stretched nearly 60 meters from bank to bank. The deck measured just over 3 meters wide. Barely enough for a truck, but sufficient. Richardson ordered one final inspection, and the engineers walked its length, tightening knots and securing the anchors one last time. The drums knocked softly against the current, their hollow sound blending with the murmuring water. After 16 hours of uninterrupted labor, the improvised bridge stood ready. It had no name, no blueprint, and no guarantee of success. To anyone unfamiliar with combat engineering, it looked fragile and temporary, a contraption born of desperation. Yet beneath its rough surface lay precise logic, calculated buoyancy, balanced weight distribution, and structural redundancy. When the first light of morning touched the water, the barrels gleamed like a row of armor plates, and for the first time in days, the river no longer divided the army. It had been conquered by hands, tools, and the sheer will to advance. At first light on the following morning, the river lay quiet beneath a thin veil of mist. The engineers gathered along the near bank, their uniforms damp from the night's labor, staring at the bridge that had taken shape out of nothing but barrels, chains, and timber. It was an ungainly thing, flexing with the current, rocking gently as water lapped against its sides. But it floated. The command had arrived before dawn. The bridge had to be tested immediately. Every minute mattered. The armored column waiting behind them had been idle for almost 24 hours, its fuel supply dwindling and its orders unchanged to advance eastward toward St. Lo. The only question was whether the improvised span would hold. The first vehicle chosen for the trial was a GMC CCKW 2.5-ton truck, standard issue for transport battalions. Its weight, roughly 5 tons when fully loaded, was enough to test the structure without catastrophic risk. The driver engaged low gear and eased forward, the engine rumbling softly as the truck climbed the wooden ramp leading onto the floating bridge. The engineers watched in silence. As the front tires reached the first set of planks, the structure dipped slightly, the barrels shifting under pressure, but the bridge held its shape. The truck advanced slowly, the timbers groaning beneath its weight, the water slapping rhythmically against the steel drums. When the rear wheels reached the far bank, a wave of quiet relief swept over the men. The span had survived its first crossing. Encouraged, Richardson ordered the next phase. A light M8 Greyhound armored car followed. It weighed nearly 8 tons and rolled low, steady hum as it crept onto the bridge. The engineers noted how the modules flexed in sequence, absorbing the weight without buckling. The floating sections dipped no more than a few inches before stabilizing. The lateral cables strained, but did not give. When the vehicle reached the far shore, Richardson recorded the deflection, less than expected. His calculations had been correct. The final test would be the ultimate proof. A medium tank M4 Sherman, over 30 tons of steel and ammunition, stood ready at the head of the convoy. No one spoke as the driver started the engine, the sound of the Continental radio roaring over the river. The tank advanced, its treads grinding softly over the wooden planks. The bridge trembled. Several barrels sank halfway before stabilizing. The timbers creaked, nails squealed against metal, and the chains holding the modules groaned as they absorbed the strain. The tank inched forward, the entire structure flexing under the weight, yet each section compensated for the next. It was not strength alone that kept the bridge afloat, but the distribution of pressure, exactly as Richardson had intended. At the midpoint of the river, where the current was strongest, the tank slowed. Water surged over the outermost drums, but they held firm. The floating surface bowed slightly, creating a shallow arc, yet the stability remained intact. Engineers on the banks gripped the anchor cables, ready to pull them taut as the span began to drift. When the tank's treads finally gripped the far incline, and the machine rolled onto solid ground, a cheer erupted from the waiting crews. Against every prediction, the makeshift bridge had borne the full weight of a Sherman tank, without collapsing. Once the crossing was proven, the column began to move in earnest. Trucks, jeeps, and half-tracks followed one after another, maintaining careful intervals to keep the load balanced. By late morning, the water surface rippled constantly from a movement of vehicles. The bridge swayed under the rhythm of engines and boots, but endured. The barrels flexed and returned, behaving like living parts of a single machine. Engineers walked alongside each convoy section, tightening cables, adjusting moorings, and inspecting for leaks. When the sun climbed higher, the bridge gleamed in its full length, a strange, floating artery of war, connecting two banks that had been impassable only the day before. By noon, the last vehicle had crossed. More than 24 trucks, several armored cars, and 4 Sherman tanks had passed safely to the opposite shore. The operation, which might have been delayed for days, continued without interruption. Soldiers on both sides of the river stopped to watch the final tank reach land. Then came a spontaneous round of applause, brief, restrained, but sincere. The men knew what they had witnessed. A handful of engineers, working through the night with no materials but what the battlefield offered, had achieved the impossible. Their barrel bridge, mocked as absurd hours earlier, had become the lifeline of an advancing army. When the last echo faded, the engineers stood by the water, watching the bridge sway gently in the current. It was scarred and soaked. The planks splintered and chains rusted from strain, yet it remained intact. The Wire, once an obstacle, had been conquered not by firepower but by ingenuity. And somewhere among the mud, oil, and steel, the quiet triumph of that moment spoke louder than any victory parade that would follow. The success of the improvised barrel bridge across the Wire did not remain an isolated event. Within weeks, Reports of its effectiveness circulated through engineering command channels across the European theater. The Corps of Engineers, constantly documenting field innovations, took immediate interest. What had begun as a desperate improvisation soon evolved into a replicable method, passed from one battalion to another through after-action reports and briefings. The innovation embodied the adaptive mindset that the U.S. Army prized in its field engineers, solving immediate problems with whatever materials the battlefield offered. By late summer of 1944, similar makeshift barrel bridges appeared in several operational zones. In northern France, detachment from the 300th Engineer Combat Battalion used seal fuel drums to construct floating rafts near the Seine for ferrying jeeps and light artillery when their pontoon sections were destroyed during enemy air raids. In Belgium, units of the 291st Engineer Combat Battalion, later renowned for their defense of the Malmedy area during the Battle of the Bulge, reported using improvised flotation devices composed of oil drums and cable to move supplies over flooded terrain in the Ardennes. Further south, in Italy, where rivers like the Arno and Po often flooded unpredictably, American and British engineers employed the same principle, building temporary raft from drums and planking to support the advance of light reconnaissance vehicles. The method was not limited to frontline use. The Corps of Engineers field manuals and monthly bulletins began to include references to improvised flotation bridges as valid temporary solutions. A 1945 bulletin from the Office of the Chief of Engineers described how sealed 55-gallon containers, properly distributed, can provide reliable flotation for loads exceeding normal field expectations when standardized equipment is unavailable. These documents cited examples from France and Italy, acknowledging the ingenuity of units, such as the 36th Engineer Combat Battalion. Although the barrel bridge never replaced the Bailey or M2 pontoon systems, it served as a crucial stopgap measure in the unpredictable conditions of a European campaign. The Bailey Bridge, a British-designed modular steel truss system, required precise assembly and vehicular transport. The M2 pontoon bridge demanded specialized rubber pontoons and heavy decking components. Both were highly effective but dependent on intact logistics. In contrast, the barrel bridge could be built entirely from local or abandoned materials and assembled with minimal equipment. It became the embodiment of the phrase, "make do and move forward," that characterized Allied engineering philosophy. The spread of the idea was accelerated by word of mouth among engineering officers. Field reports circulated through Army newsletters, and photographs of vehicles crossing crude, barrel-supported spans reached command posts. Some divisions in the U.S. Ninth Army even experimented with hybrid structures, combining standard Bailey Bridge trusses mounted on rows of fuel drums when pontoons were insufficient. The adaptability of the design made it especially valuable during the rapid river crossing operations of late 1944, when weather, flooding, and destroyed infrastructure slowed the Allied advance toward the Rhine. British and Canadian engineering units, observing the American improvisations, adopted similar methods during the winter campaigns. Reports from the Royal Engineers 79th Armored Division mention the use of sealed petrol tins and small oil drums lashed together to create auxiliary floats for bridging under fire. This shared experimentation across Allied forces reflected a broader pattern. As the war intensified, innovation no longer flowed only from headquarters to the field, but also from soldiers upward, shaped by necessity and experience. By the time Germany capitulated in May 1945, the principle of using industrial containers as flotation support had entered official doctrine. The U.S. Army Engineer School at Fort Belvoir included the barrel raft bridge, among examples of adaptive engineering solutions in its post-war training materials. In 1947, during the publication of revised manuals, the technique appeared under the category improvised bridging equipment, emphasizing its role as a temporary yet effective solution in combat operations. Beyond the war, the idea persisted. In the Korean conflict of the early 1950s, American and South Korean engineers built makeshift river crossings using oil drums, steel pipes, and salvaged aircraft fuel tanks, descendants of the same improvisation that had been tested on the Wire. The concept of modular buoyancy using standard containers became part of the engineer's toolkit, influencing designs for post-war civil defense and disaster relief operations. Thus, Captain Richardson's solution transcended the immediate battlefield. It symbolized the ingenuity of wartime engineering, the ability to turn refuse into infrastructure, scarcity into invention. Though it never carried the prestige of the Bailey Bridge or the fame of the pontoon treadway, the humble barrel bridge left an enduring mark on military engineering, a testament to how imagination, under pressure, could reshape the boundaries of the possible. In the years that followed the war, the story of the barrel bridge crossed from battlefield memory into the institutional history of the U.S. Army Corps of Engineers. The principle it embodied, adaptation through necessity, was studied, formalized, and preserved as part of the doctrine that defined post-war military engineering. After-action reports from Europe were compiled at Fort Belvoir, Virginia, the center of the engineer school, where officers dissected every successful field improvisation from the campaigns in France and Italy. Among them was Captain John Richardson's design, noted not for its elegance but for its unorthodox practicality. The bridge of floating barrels, once dismissed as absurd, became an official case study in creative problem-solving under pressure. In 1945, the Corps of Engineers published a comprehensive revision of its wartime manuals. The document, FM5 to 270 Bridging, and later supplements issued in 1947 and 1950, incorporated a new section titled Improvised Flotation Equipment. The manual described, in simple technical language, how sealed 55-gallon drums, aircraft fuel tanks, and even airtight containers could be configured as buoyant supports for temporary bridges and rafts. It referenced field reports from units, such as the 36th Engineer Combat Battalion and the 291st Engineer Battalion, whose experiments had proven the feasibility of such designs. Richardson's rough sketches, preserved in the battalion's operational diary, were redrawn into a standardized diagram labeled Barrel Raft Module. Beside it, an instructor at Fort Belvoir had added a handwritten note. Works against logic, but works. That phrase captured the spirit of wartime engineering better than any official slogan. It reflected the essential paradox of the field engineer's craft, the reliance on science guided by intuition. Soldiers who had served in Europe often spoke of ingenuity as the most valuable weapon they possessed. In interviews recorded for the Corps' historical branch, veterans described how improvisation became second nature, turning scrap metal into bridges, oil drums into boats, and wrecked vehicles into recovery platforms. For many, Richardson's bridge symbolized that transformation of ordinary objects into instruments of survival. The post-war years saw this mindset influence not only military construction, but also civilian disaster response. In 1948, the U.S. Army Corps of Engineers deployed improvised drum pontoons for flood relief operations along the Mississippi River, applying lessons learned in Europe. In Korea, between 1950 and 1953, engineers from both American and South Korean units again used fuel drums and pipes to build temporary floating bridges when supply lines failed to deliver standard pontoon sets. These structures, though more refined, were direct descendants of the improvised crossings pioneered in Normandy and northern France. At Fort Belvoir, Richardson's bridge became part of the standard curriculum for junior officers. Training exercises included scenarios that required cadets to construct a functional bridge using nothing but locally available materials. The barrel bridge was no longer a desperate improvisation. It had become an example of applied ingenuity, a teaching tool to remind new generations of engineers that creativity was not a luxury, but a duty. Photographs of the original structure were displayed in instructional exhibits alongside more formal designs like the Bailey and Treadway bridges. Even decades later, the legacy endured quietly in the Corps' culture. Veterans of the 36th Engineer Combat Battalion often referred to the crossing at the Wire as their proudest moment, not because of its scale, but because it captured the essence of their profession. In their reunions and oral histories, they spoke of how the barrels creaked under the tanks and how every man on the bank held his breath, waiting for disaster that never came. For them, that bridge represented faith in human resourcefulness, the conviction that intelligence could triumph over scarcity. In the archives of the U.S. Army Corps of Engineers today, the wartime engineering reports still bear the traces of those improvisations. Between precise measurements and typed equations, handwritten annotations appear. Use whatever floats. Check local materials. Barrels can work. These marginal notes, often overlooked, reveal how the engineers of World War II bridged the gap between theory and necessity. The story of the Barrel Bridge endures not merely as a technical footnote, but as a testament to a generation that rebuilt the world with what it had on hand. It stood as a quiet reminder that true engineering was never confined to laboratories or factories. It lived in the mud, the rain, and the calm conviction that even the most illogical ideas could, when tested by courage, hold firm. The story of the Barrel Bridge revealed that engineering, at its core, was not merely a disciplined calculation, but an act of faith in human capability. It existed somewhere between science and courage, between reason and instinct. Captain John Richardson's bridge had not been a monument to ingenuity in the traditional sense. It was never meant to endure or to impress. It was a structure born from desperation, built with the simplest of materials, yet embodied a profound truth that progress often arises from moments of scarcity rather than abundance. When all formulas seemed to suggest failure, the bridge stood as proof that human intuition could still find equilibrium where theory faltered. The floating barrels were not symbols of strength, but of resilience. They swayed, groaned, and bent under the weight of war, yet they carried men and machines forward. In that trembling structure lay the essence of wartime engineering, a balance between fragility and resolve. Richardson's design demonstrated that courage in engineering was not about defying danger, but about trusting one's understanding of the physical world, even when every condition opposed it. He and his men worked without guarantees, guided only by their craft and the quiet conviction that their solution, however improvised, could save lives. The bridge on the WWII was temporary. It was dismantled after the advance moved east, but its legacy endured in the way it reshaped how engineers thought about possibility. It proved that logic could coexist with imagination, that invention could emerge not from abundance, but from necessity. In an era defined by mass production and industrial precision, this fragile span of barrels reminded those who witnessed it that innovation was still a profoundly human act, rooted in creativity, resourcefulness, and a refusal to surrender to circumstance. War had a way of reducing everything to essentials. Steel, timber, rope, and air, these became the vocabulary of survival. Yet behind the material stood something less tangible, the human will to adapt. Richardson's bridge was not simply a tactical success. It was an ethical statement about the role of intellect under pressure. It suggested that engineering was, in the end, a form of hope, an attempt to impose order on chaos, to make meaning from destruction. It was not the triumph of machines, but of minds that refused to be limited by them. After the war, as the world rebuilt itself from ruin, the same principles that guided those engineers guided nations, to take what remained and make it serve a new purpose. The Barrel Bridge thus became a quiet metaphor for reconstruction itself. It showed that broken things, discarded materials, forgotten ideas, exhausted people, could still carry the weight of renewal. It taught that knowledge, when joined with imagination, could transform even the remnants of conflict into foundations for peace. In the mud of the small French riverbank, amid exhaustion and ruin, a handful of engineers had unknowingly created more than a bridge. They had demonstrated the essence of the human spirit's resilience, the capacity to build something functional, meaningful, and enduring from what others considered waste. The barrels floated not only because of physics, but because of belief. Belief in the capacity of human reason to find solutions even in the most irrational of circumstances. In the end, the story of the Barrel Bridge was less about wood and steel than about perception. It showed that true engineering begins where certainty ends. Every war, every disaster, and every challenge that followed carried echoes of that lesson. That courage in the face of the impossible is as vital to construction as the materials themselves. Richardson's bridge did not defy logic. It expanded it. It proved that what appears absurd can become the most rational act of all when guided by necessity, intellect, and quiet determination. In that sense, the trembling bridge across the WWII was not a structure of barrels and boards, but manifestation of the timeless truth that human ingenuity, even when born of desperation, can still carry the weight of a world in motion.